Hi, this is The Register and I'm Danny Bradbury. You know, it seems as though server PC technology advances just as fast as desktop technology these days, and Intel's pushed the envelope yet again this year with the E7 family of Xeon chips. So I travelled to Hillsboro, Oregon to speak to Dylan Larson to talk a bit about what's going on.
We launched the E7 series, which is for the 4-socket and above space, so all targeted at kind of high-end database systems, high-end mission-critical systems based upon a microarchitecture that has massive amounts of memory and computational capability.
Okay. How does it differ from previous chips that you've launched in the Xeon line?
So I guess a couple of the big ones, it's obviously continued performance improvement. So we've improved performance 40% over our prior generation in that class of product, the multiprocessor product line. And it has been also just a massive memory accesses that have been added to the new product, up to 2 terabytes of memory in a 4-socket system. So just continuing on that treadmill of continuing to drive more and more performance capability, but also memory scale to meet the demands of large database and big virtualization deployments. One of the things we see significantly is in virtualization is a huge capacity for memory required. And part of that is just people are putting more and more virtual machines on their servers, and the more virtual machines, the more you have this expectation and dependency on memory to deliver performance and the capability. So what we've seen is memory is one of the big drivers, as well as high performance to manage the amount of scale. So people are getting to these consolidation ratios, which was sort of 4 virtual machines to 10 to 12 virtual machines and more per server. It's not so much that the applications are all that new, but it's as the scale and the demands of the infrastructures have grown so much. So you think about large database deployments, for example. I mean, the amount of data being stored on storage devices and amount of data being accessed by enterprises is just growing at a ridiculously high rate. So, there's recent data that came out, a Cisco report, like 1,000 exabytes or a zettabyte of data had traversed the internet last year. And just sort of this tremendous growth in data, video formats and things like that are putting much higher demands on the ability to access and store and communicate this kind of information effectively. So I think what we've seen is that this next generation with much, much higher performance, much higher memory addressability puts you in a position to take full advantage of the kind of data that you have stored in your infrastructure.
Okay, and tell me about the history of Xeon. When did it start and how has it evolved over the years?
I think Xeon kind of has its genesis, its sort of roots around the P6 architecture, which was kind of in the late 90s type of environment where we had made just a substantial improvement in the kind of performance, kind of brought the microprocessor to an amazing capability, and the very large cache architecture that was in the Pentium Pro architecture in this time frame was the genesis for what would become Xeon. And I think what Xeon started out as a new class of product to address what was really largely proprietary architectures and bring the horizontal economics of the Windows and Intel and eventually the Linux environments versus a very sort of integrated proprietary stack.
You went to a 32 nanometer process with this particular family of chips. What does that bring you?
Bringing 32 nanometer to the Xeon product line, bringing 32 nanometer to the E7 products, for example, is all about how do I put more and more capability within the footprint that I have. More transistors to do bigger cache sizes to accelerate performance, more computational capability, more cores, more floating point acceleration capabilities, and more new feature sets like new instructions for AES encryption or new instructions for trusted execution, those kind of elements, as well as new capabilities for reliability and the way we address large pieces of memory. So with 32 nanometer, you get much more capability, but you also get advances in the energy efficiency for that new space. As you pack more density, you also get advances in efficiency, reduce power consumption, and meet the thermal envelopes that are expected in those timeframes.
Talk about some of the advanced features that we'll see in the E7s as they start to appear in products.
This memory buffer technology called SMI, which is a symmetric memory technology, which allows you to get a lot more scale to your memory architecture. And that's been a part that's been, the code name was Millbrook at the time, which was a lot of press around. But ability to just get much larger scale, but at very high speed as well. So you're not compromising the performance with the amount of capacity in your platform. You can get the maximum out of it. I think that's one. I think the other big area is around reliability features, the RAS capabilities that allow us to do machine check architecture, which actually recover from what could be pretty catastrophic types of errors, as well as double data corruption errors and things like that. So managing just the uptime and reliability of the server has been a big source of innovation and focus.
In previous versions of the Xeon chip, Intel included something called Error Correction Code, or ECC, which helped to correct any errors in the internal communications of the chip. With the E7 range, it has included a new type of technology that enhances this error correction.
Double data correction technology, which is about managing multiple bits of error that you would find in your platform. So similar approach to ECC, but quite a bit more complex, because anywhere within that block you can have an error, and you have to be able to detect it and correct it effectively.
Why do these errors occur, just from a layperson's perspective?
They're much more common than I think many people expect, and I think there's been very wide, sort of advocacy for ECC memory across the server line. I mean, we've even seen Microsoft come out and say ECC should be even broader; it should be everywhere, because these errors do occur. But they occur for a myriad of different reasons. It could be things that are just some mean time to failure kind of environment, that is some physical problem in the hardware. It could be a software bug that's leaking memory in different ways. So there's a number of different places that it can occur. The good news is we have a series of schemes that can address the correction of that very, very effectively.
What are you doing to make green data center managers more effective with these chips? How are they supporting lower power footprints?
Power management, I think, is obviously a huge thing that people are more and more worried about and focused on. One of the things we've done is, of course, we've moved from kind of ramping pure frequency to ramping core count and innovation around how we maximize performance within the fundamental elements that you deliver in a microprocessor, so addressing all aspects of that. At the same time, we've got a big focus on how do we manage the amount of power that we put into the system, and then manage what the power is used while the system's operating. So we talked about power states within the system, and power gating within the system to kind of cordon off elements of the processor that don't need power and bring that power levels down. And then for areas that are workloads that are decreasing requirement, can reduce power as well, or we put the system to lower power states for standby, for example, as ways to just manage the power most effectively through just being much more deterministic about how you power things down and based upon the need in the system. We've also developed this technology called Turbo to allow us to actually exceed some of the stated gigahertz of the product for periods of time by taking advantage of headroom that's available within the system. So actually getting work done faster in some cases, and then back down to lower power states. So it's all about how do you take advantage of what's resource available within the server to maximize your work as well as the efficiency of the system.
Talk a bit about the AES on-chip encryption that we're seeing in this latest version of the Xeon family.
Yeah, I think, no question, and I think that you read the paper daily, and security threats continue to be kind of one of the top, both noticeable things, is also maybe one of the big worry beads in the industry, because absolutely a major threat. If you're going to have massive amounts of data, your own personal data in places, it seems like it's time to really understand what you can do to address the security challenge. So what we did is we looked at the common algorithms for cryptography, the common algorithms that support the security transactions in server space, and one of those things is around AES. And it's an interesting thing that AES new instructions are a series of new instructions that we put into the microprocessor to accelerate the mathematical processes to do block cipher, block encryption, and elements like that to get up to, depending on the process, 10x faster performance kind of things for these kinds of cryptographic processes. And I think part of it is just this path of how do we bring more value beyond cores and frequency and sort of optimizing for maximum performance, but also optimizing for additional capability. And one of those things is these new instructions for cryptographic processes. And you can envision a continued evolution of that capability over time.
Talk a bit about Itanium. We know that, of course, Oracle has decided not to support Itanium with its database products. What impact has that had on Itanium customers at the low end, perhaps bleeding down and deciding to use Xeon at the high end?
We haven't seen an impact yet. I think it certainly has created a level of anxiety, just to be direct, with some of our customers. But I do think that it has been an area that has been a big source of investment for us, working with the software players like Oracle and others, of which there's thousands and tens of thousands of applications that are written for Itanium today. So I think it's an area we're going to have to continue to work through with our customers to make sure we move things forward. But it was a disappointing position that caught us in a position that we were not really very, very pleased with. And I think what we find is that they're positioned very, very differently in the market. I mean, I think that Itanium has been a big driver of a lot of this risk migration activity, and has been a big focus with a different type of architectural approach, different set of programming characteristics, and then Xeon being kind of building on that Intel instruction set that's been around for quite some time. But I think that they're feeding different parts of the demand. I think the consistent thing is people are looking at larger and larger systems, especially in the E7 case, and how they produce capability to address large amounts of memory and build big database accesses. But I think what we see is we still continue to see Itanium used in many, many places for that mission-critical sort of risk migration environment. We're also seeing a lot of risk migration opportunity in the traditional Xeon line as well. Yeah. Big thing between Itanium and Xeon is all about OS choice. You look at elements of Itanium architecture where OpenVMS and HPUX have been sort of traditional legacy Unix operating environments that are still well deployed and in use today, as well as Xeon product line where you see Linux and Windows and adding a whole bunch of new mission critical RAS features to that product line as well to meet the diverse needs of customer choice with mission criticality.